Yeah. Now can you hear Ramprasad? Yes. Okay. It keep going out first. Okay. Right. So now can you hear Ramprasad?
Yeah, I can hear it, but I can now the video is off though. Okay. Yeah, I can hear it, but I can now the video is off though. Okay.
Click here. You want to.
Okay. No, it won't. Happy, can you hear us now? Can you see the?
Yeah. Now I can hear it properly.
Okay, sorry.
Yeah, thanks a lot. Sorry about it.
You do. Lucky for us. Right.
No, it won't.
Happy, can you hear us now? Can you see the?
Yeah. All is fine. Yeah.
Okay,
Thanks a lot. Sorry about it.
You do. Yeah, that'll be fun. I don't know if that's any question. Yes. Everything is fine. Best of luck to us. Right. So there are various ways of doing it. One well-studied way of approaching this problem is to say that, okay, so you look at the utility function to, or you restrict the utility function to what I call these pairwise separable utilities, which is to say that you think of these, so there are n players. You think of these as each player playing a two-player game with every other player. He gets some utility function, so that is this partial utility function that depends only on the pair of strategies. And then you simply add up everything that you get. So this is one way of doing it. These are called polymatix games. These are very well studied class of games. And here, of course, the representation is much better because now you have, well, you think of these as these matrices, right? So you have like a k squared entries. So 2 times k squared, and there are n squared such cases. This is one such class which is well studied. Of course, there are many other classes. There are what I call condition games. Condition games again are strategic form games, but you don't really have to provide the strategic form game explicitly. You present what are called these condition models. The derived strategic form game is like implicit, so that is exponential, but again, condition model itself can be given in a context. There are also, so if you're looking at coordination games or coalition formation games, there is this class called additively separable hedonic games, which is also very well said. Okay, so this entire, so all these examples, all these approaches is to deal with, so these are quantitative payoffs, these are numbers. Right? So, and some way of restricting these quantitative so that you get some compact approach. Another approach to kind of achieve the same thing is to look at quantitative payoffs or use some sort of a logical language to represent the goal formulas. Yeah, so this also there's a long tradition of doing this. This is inspired more by computer science rather than game theory. So in computer science, there's a long tradition of doing it. So for instance, there are these infinite games of graphs where the objectives are given as omega regular conditions, or you can think of it as linear time temporal logic conditions. That's one way of thinking about it. So these are repeated games infinitely often. But if you're looking at this one-shot game, the kind of things that I'm talking about, you can also give goals as Boolean formulas. Okay, so that's another way of doing the same thing. So these are called Boolean games. So I will come to that in a minute. So what we are looking at is a model which is very similar to Boolean games. The setting is very simple. So you have a set of n players, a finite set of n players, and there is a finite set of propositions. Now the set of propositions are partitioned into n. So it's like each player is associated with some set of propositions. Yeah, so there's a finite set of players, and each player is also associated with a finite set of propositions. You know? So typically in Boolean game, the way it works is these players kind of control those propositions, so you can choose a valuation for the proposition. So that's the strategy of a player, to choose a valuation for that set of propositions. So here, that's not what we're doing. For us,
What is the proposition? Is it a
it's just a Boolean variable.
just a variable?
Yeah, it's just a variable which takes 2. Right. So just think of it as a Boolean variable, right? Right. So the strategies in the setting that we are looking at, it's more based on communication. Okay, so you have a set of propositions. You also have a valuation. This is like somebody picks a valuation. Think of it as a nature picking a valuation. And the strategies of the players are to decide whom to reveal these propositions to. So it's like each player controls a set of propositions, but the control is really whom to reveal it to, right? Not the valuation as such, but whom to reveal it. You know? So formally, this a strategy would be for player I would be a function which specifies for each player the subset of proposition that it reveals. Okay? So in some sense, so something like this. So Si of j is saying that, well, player I is revealing to player j some set of propositions. Yeah, so the valuation is fixed. Think of it as the valuation being fixed, and then I am telling let's say Shibaki some subset of the values of my propositions. So these are the values.
So the propositions, as you say, it's partitioned across the
Right. So these are
layers, and
right.
if you are the owner of some propositions, then you can reveal only a subset of the propositions that you own.
Right. Yeah. So you can only reveal the propositions that you own. You can choose to reveal. So, for instance, extremes, right? You can choose to reveal nothing. Yeah. So this is that SI empty set notation. Or you can. So this is like absolutely no information, and or you can choose to reveal everything. So this is like the SI for all, which is like perfect information. So in general, you can choose to reveal a subset of these propositions. Okay, so one reason why we are doing this is
You didn't specify utility.
right. So I am coming to that. If you look at strategy games, I mean these are imperfect information games because all players are supposed to choose a strategy simultaneously, right? So inherently these are imperfect information games. What we are modeling here are what are called incomplete information games. It also has imperfect information because everyone has to simultaneously choose. But it also incorporates incomplete information because this valuation, as I said, it's like someone picks. Yeah, these are not. So the players don't pick this. It's like think of it as a nature's move. Yeah. So the point is the utility function itself is not common knowledge because of this.
It's also done, the valuation is chosen simultaneously with the,
No, so the think of it as valuation being fixed. So I'll come to how it's chosen.
so it's chosen and then everybody knows it.
Right. No, so so you only get to know the value of the propositions that you have.
Okay.
So
Who controls what?
that is known. So at this point, our assumption is that the
Partitions.
P's are common knowledge and the partition is also.
So the
Yeah,
player is
that's
a
a-
part of the game instance. Is V also part of the game instance?
So right. So let me define that.
Okay.
Yeah. So okay. So now once you have a valuation and a strategy profile, again a strategy profile is just a profile of these functions, right? Once you have a valuation and strategy profile, then it induces an observation relation, that is equivalence relation over valuations. So basically, whatever the propositions that are associated with me, I can see, and the rest I cannot see unless that person reveals it. Right. So whether it is revealed or not is determined by this profile. Okay. So what is this equivalence relation? Well, it's very simple. So you just look at, so this is a profile of strategies. This is a strategy profile, right? So Pi of S, let's just denote it by all the propositions that player I sees. Of course, player I sees all the propositions that it controls, and also whatever is revealed by others too. Right? That's the set Pi of S. And two valuations are indistinguishable for player I if what he can see are the same. These two valuations. So that's it.
What is there like in
Right. So S is a profile of strategy. So it's like a tuple of these functions.
Okay.
So each function tells what that player reveals to the others. Once you have a tuple of these functions, you can figure out what player I is being shown by the others, and you just take the set of all these variables.
The union of the SGI.
It is the
Yeah, it's the union of the SGI to
this one, is that?
Yeah.
Right. So it is it is a set of all propositions that somebody shows. So there exists J such that
Yes, so the union
for
of
all the zero.
right, yeah,
and your own.
and your own. Yes. Okay, so right, so this is the kind of the game that we are looking at. You have a set of players, you have these propositions which are partitioned among these players, and we have some logical language. So I'll formally define what this language is. So you have some formulas which specifies the goal. Okay, and so these are formulas from some logical language. And the idea is you can interpret these formulas over the valuation and the strategy profile. So the semantics of this language is defined in terms of the valuation and the strategy profile, and you have a notion of when the valuation and the strategy profile satisfies the formula. Okay. So once you have that, the utility function is very simple to define. Well, the utility function is either 0 or 1. It is 1 if the formula is satisfied, the goal formula is satisfied, and it is 0 if it is not satisfied. So that's the definition of the utility function. So all this is based on fixing a valuation. Right? If I don't fix a valuation, then there are various possibilities, right?
So I'm a bit confused. So the formula is only on the propositional variables?
I have not defined the language yet. Yes, it is only in the propositional
Then
variables.
why do you need S?
Right, so I will define the language of the logic in the next slide. Yeah, so it is a language where you can interpret it over this pair of valuations and S.
No, ACE is the strategy.
S is the strategy profile. What
So it will say what others are revealing to you. And
Yeah. But why does the,
Yeah, so if you can wait till next slide, then I'll formally define it. That's because we are putting in an adjustment operator. So that's essentially that. I'll formulate that. Right. So assuming that there is such a notion of there's a language and there's a semantics which depends on the valuation and what show, then the utility is defined in the simple way where it is one if formula holds, otherwise it's right. So now once you have this, again, the notion of an Nash equilibrium is standard, right? I just lift the same definition, right? I have a notion of I've defined what is the utility, and then I just lift the same definition. That's the Nash.
For every valuation or
Right. So this entire slide is when I fix a valuation, right? But now the valuation is not fixed, right? So then right. So what you have is, so this is what we call a Boolean conservation game, which is this this structure where you have a set of players, you have this partitioning, and you have a goal formula for each player. Now, when the valuation is not fixed, the players want to choose a strategy, which is well, for each valuation you can pick a strategy, right? That's what we call a uniform strategy. Except that I mean, in the valuation, you see whatever the propositions that you own, you can see the values. But then you cannot distinguish between certain other propositions, right? So the strategy that you pick should be uniform under these indistinguishable valuation. That's all. So uniform strategy is a map which is from a set of valuations you can pick a strategy. Except that it has to have this consistency requirement that if you cannot distinguish between two valuations, then the strategy that you pick should be the same.
but this equals only with PI, not the observation.
Yeah, it's only with this.
But this also depends on the strategies of the other players, right? Like,
No, this
No, this one does
strategy,
not.
right?
Yeah, so this one does not. The utility will depend. So the gammas will have something to do with
I
that.
mean, so you cannot distinguish, if you say you cannot distinguish the valuation, it also depends on what the other players are revealing to you.
No, so that it comes in the goal formula, the interpretation of the goal formula. This is like, so it's a one-shot game, right? You have to pick your strategy. So what you can do is pick what is a uniform strategy, which is like a function for each valuation. I pick something. Except that I have to be consistent. That if I cannot distinguish between two valuations, then I have to pick the same
So
strategy.
initially there's some equivalence classes, then they get
defined
defined further when you get reviewed.
when you get to have that communication.
So I'm guessing that.
Yeah. So
Initially you have you know the values of some of the variables. And then you choose your strategy to, as in what to reveal your home.
And then the goal is
evaluation
evaluate
happens,
from
and
the-
then you get multiple
On
points,
the-
and then you
So it's essentially a refinement test. Okay, so there is one particular kind of object here which is of interest, which is to say that well, I don't really care about, so I'm going to pick the same strategy for every valuation. So these we just call it as a globally uniform strategy, which is that I don't distinguish between valuations, whatever it is, I just pick one strategy. Okay, right. So now with this interpretation, what happens to the utility function, right? So because you have multiple valuations, for each valuation you get a utility function. So what you get is a tuple of utility functions where the size of the tuple depends on the indistinguishable valuations. So for each indistinguishable valuation, you get some utility function, either 0 or 1. Okay, so if I can, so this is like a tuple. If I can define some notion of ordering over these tuples, then I can just lift all the definitions that I had in terms of Nash equilibrium methods. Right. So earlier you had one number, so the ordering was obvious. Now I have a tuple of zeros and ones.
Where you said this, what is the expectation over here?
Right. So I'm just using the term expected outcome, so there's no expectation. So this this is a function of this form. This is a uniform strategy. Yeah. And so sorry, this should be a uniform strategy profile, and this is a valuation. Yeah. Now, so if you fix a valuation, then you have either a 0 or 1, depending on whether the goal is set. Right. Now, the valuation is not really fixed because you'll have to look at all possible valuations that you cannot distinguish.
Yeah, in the class.
In that class. So what you essentially get is a tuple of these ones and zeros. So that's what we called expected outcome.
It's
So it's
report
just the entire total. It's not one number, it's just the entire. Okay, so now any way of, I mean, whatever is, so you pick a definition of how you want to compare these tuples. So essentially you want to define an ordering on these tuples, whatever is the ordering. Once you fix that ordering, you have the notion of Nash equilibrium and everything as it was. That's all. So earlier we had one number. So now you can aggregate everything into one number, or you can pick some ordering of these tuples. That's it. You can just lift everything that.
So I think like is this, so what are the elements in the tuple?
It's just zeros and keys.
Yeah, but what is the length? What is the length?
Right. So the length depends on how many non-distinguishable values there are. Okay,
So as a uniform strategy, then does the vector entirely consist of same element? I mean,
Each player
No, even then, so even if S is uniform,
Yeah.
you are only, there may be valuations that you cannot differentiate between because you don't see those variables. So then the tuple is 2 to that many variables.
Yes.
okay. No, what I was asking was, does the vector just have the same value if S is uniform? But I don't think even that is true.
I don't know.
No, so
the
this-
outcome depends on all the variables.
Yeah, right. So depends on the other.
And this sign, you mean a total order, partial order?
Yeah, so total order is ideal.
Yeah.
But you can define it, so whatever works for Nash equilibrium. So if Nash equilibrium is a solution concept that we want to study, then you need to somehow define not greater than. Yeah. So any way of defining a not greater than will work for that definition. Okay, a strict order is easier to comprehend. So what we do is.
Okay, can you just go back and show me the definition of utility once again? How do you define
Yes, so it is just on whether the formula is being satisfied or not. So the goal is given as a formula.
So what does that mean? Like, how does the formula depend upon S?
Right, so I'll define it. Let me define it here. Right, so the definition of Nash equilibrium remains the same, except that you need to somehow define this operator here. Right? So there are various possibilities. I mean, so we for this point we just pick two simple notions of comparison, which is to say that okay, you just look at a max value. So that is one option. Look at the max value of this vector. If the max is better in S as in S prime, then you say that the utility is better, right? This we denote it by the optimist rule. Of course, you can look at the min of the vector, so that is just the pessimist rule. You can give anything, right? So as long as you can give a comparison between these tuples, you can use that. That's now once this comparison is defined, then you can look at the set of Nash equilibria, which is based on whatever is the outcome rule that you get, right? So for pessimists, this would be the set of Nash equilibria. For optimists, something like this would be the set of Nash equilibria, and so on.
So these are all partial orders.
So this would define a strict order because you're picking one number, right? The max.
Yeah, but two different tuples can have the same minimum. Then
Yeah, correct. Yeah,
it will not.
yeah. But you just need a comparison operator for defining this. For this defining the Nash equilibrium.
Somebody may have a question.
I don't think something because 9 messages are the full.
Yeah, this came out like, okay,
Okay, so
So I mean, so these two vectors in vector range, they could have different sizes also, right?
they could have different.
And I'm not clear what it means by a set of. Okay, so you're defining a Nash equilibrium, but really this vector dominates every other vector. You see.
So I still have to tell you what that formula is and how to evaluate that everything. Okay, so right, so
And does this give you a lattice? Like, what does this give you? Like, I mean, this is clearly not a total order, right? So what does this partial order look like?
So it depends. So we are looking at these two.
Because we have, right,
This optimist and pessimist. It depends on what rule we fix. Okay, so there's one more notion of Nash equilibrium which is interesting, which is to say that it's like the X force equilibria, which is to say that, okay, so this is a very strong notion, which is, it says that it's a profile where even if you tell me the valuation, I have no profitability. So it's saying that it's a profile S. If no matter what is the valuation, in that game where you fix that valuation, you still have the S of B is an Nash equilibrium in that game. So it's a profile where even if you were to tell me the valuation, I still don't have a profitability. So that's like a very strong definition. So if something is a maximal Nash equilibrium, of course, it's going to be a pessimist and an optimist. And so these are the three things that we essentially look at: pessimist, optimist. The main reason why we speak to pessimist, optimist is because the definition is simple. But also we want, at least for this purpose, we want a qualitative notion. You can look at taking averages or whatever, right? So these become more quantitative. For this purpose, we wanted to stick to a maximal is like the strongest. So if you have some results on maximal, that kind of encompasses both pessimist and right. So now let me just quickly tell you what is the language. So language is very simple. It's almost like Boolean. So this is the part where it only depends on the valuation. But then I'm adding epistemic operator. These are called knowledge operators. So this is like Ki of alpha essentially says that agent I knows alpha. You know, agent I knows alpha. Well, if he so the formal definition or the semantics of this knowledge operator is saying something like. Think of it as a set of words, right? And there's an equivalence relation over the set of words. Yeah. And you evaluate the formulas on these words. An agent knows a particular property holds if among all the equivalent words for that agent, that property holds. So that's the standard definition of this epistemic operator. In this case, so this is just Boolean. This is all evaluated essentially on B. Right? I mean, it's nested. So once you put in the KI, you need both, but essentially these are all Boolean. So VS KI alpha, this is the part where S is being used. This holds if and only if for all W where you cannot distinguish or player I cannot distinguish between B and W under the refinement S. This is where the strategy profile comes in. Under the refinement S, alpha holds. So you look at the strategy profile, you look at everything that everyone has shown you, and under that refinement, you look at all the valuations which you cannot distinguish everywhere alpha. Then I know that alpha holds. So that is clear. So a very simple Boolean language with the KI operator. That's essentially the both.
Yeah, so isn't KI just a big hand or something? Why do you use separate operator?
Because of this, I mean, you are iterating over
other values overall, a big hand overall, like a group in the class.
Well, that is not part of the language, right? So you have propositions. So the language is built on the propositions. The valuations are semantics. So I can't put in my formula, I can't put a conditional words. So I can only put conditional words.
So here the words are the valuation.
Right. These are the valuations.
So write this, you don't need to know about the other pairs. So you can write KI alpha without actually fixing without the size of the domain is what is it.
So there is one particular fragment of this which is interesting, which is, I mean, this I can see KI is something very standard in model logic. This epistemic operator. There's also a very standard operator which is studied in model logic, which is saying that so it's called the knowing whether. So it's saying that the actual value of alpha I don't care. Yeah? It's only whether it's only about knowing whether alpha is. So in some sense, if you think of these as propositions, right? The value of the proposition does not matter, whether it's true or false, but I should know that proposition. So if that proposition is controlled by someone else, then he should have shown me that proposition. So that is what matters. So if he does not show me that proposition in that S, then knowing whether KW of that P does not hold. If he shows me, then it holds. So the whether it's true or not, true or false is zero. Okay, so So I hope this is right. So just to run through a simple example. So here is a two-player game where you have let's say one proposition controlled by player 1P and proposition Q controlled by player 2. And here is just a coordination game where both of them have the same goals. So I mean, it's a very simple thing that I'm writing. I'm just taking conjunction. So these are all conjunction over. So on this side, essentially, I'm enumerating all possible valuations, and then taking the conjunction over there. Okay, so in this game, so each player controls one proposition, right? So for player 1, for instance, he cannot distinguish between these two valuations, the valuation where P is true and Q is false, and the valuation where P is true and Q is true. He cannot distinguish simply because he cannot see. So now if you take the min over, so the min over U1, right, for this particular goal, then what you get is 0. Right? Because here I am just enumerating all possible valuations, right? So there is always one which is a possibility. So that means, I mean, this is for all x, right? So that means any profile is going to be a Nash equilibrium. So this is true for player 1 and player 2. So any profile is a Nash equilibrium because the mean is always going to be 0. And that's the case for the optimal decision rule also, because the max is always going to be 1. And therefore, the any profile is going to be a Nash equilibrium according to the optimal rule. But if you look at the maximal Nash equilibrium, then it's going to be this. Right? Because if I know the valuation, then I always have a deviation. Right? Whatever is the strategy you pick, if I know the valuation, then I always have.
So why do you have a deviation? Like
because the way this is set, right? So for instance, if P and Q are true, then this is saying that player 1 wants to know Q, which is controlled by the other player, and he wants to reveal P to the other player. Okay, and then these are the contradictory.
okay, can you also say the semantics of the second line? Like what
This
is
one. So if P and if P holds and Q is, so if P is true and Q is false, then so it's like saying I want to so player 1 wants to reveal P to player 2.
Okay.
That depends on whether Q is true or Q is false. Yeah, but you can't see Q because Q is controlled by the other player.
So what does the negation of K2P mean?
It means that player 2 does not know P.
Player 2 does not know. And so K1 of negation Q means player 1 knows that Q does not hold true.
Correct. K1 not Q means player 1 knows that negation of Q.
But Q does not belong to player 1, right? So player 1 doesn't have the knowledge of Q.
Right. I can always write these formulas.
Okay.
You're talking about the interpretation.
I see.
Yeah. So in terms of writing these formulas, there's no problem.
Okay.
So it can be over all propositions. The interpretation is okay.
So when you say that PQ is equivalent to P, would you actually give me a strategy profile as well? I mean, the for all strategy profile is very known, right?
Say it again. No, so this what I mean is in terms of the valuation, right? So this is the initial without the refinement part.
Okay.
Yeah. So I cannot distinguish between the valuation where Q is true and Q is false. P, of course, I know because
Okay.
Right. So this is without the refinement.
I mean, before the
messages are before the messages are.
Okay.
Okay, so another simple example. So in some sense, this is like the matching penny. So this is again, you have two players, two propositions which are controlled by each player, and the goal formulas are something like this. So for player 1, it's saying that I want to reveal. So if the other player reveals Q, then I don't want to reveal P. And if the other player does not reveal Q, then I want to reveal Q. Similarly, for the player 2, where he wants to say that if the other player reveals P, then I want to reveal Q. If the other player does not reveal P, then I don't want. So this is like that matching penny stuff. Okay, so here again, there is no maximal Nash equilibrium because whatever you pick, you have a better start, right? And if you look at the globally uniform study profiles, so these are like profiles where we just pick one strategy, right? No matter what the valuation, we pick one strategy. You can see that there is no pessimist or optimist because well, you will have a deviation if that's if it's a globally uniform strategy. But what is interesting here is that here is another profile where this is not globally uniform. So player one can, for instance, say if P is true, then reveal P. If P is false, then hide P. Player two can also say the same thing, right? So reveal Q and reveal hide Q depending on whether Q is true or not. Now, if you take a combination of these two uniform strategy profiles, then the min is going to be 0. Right? So no matter what the other guy picks, I mean, there's always one where it's going to be. And there's no profitable deviation, right? Because whatever you pick, so if player one deviates, right? No matter what it is, because of this, because of the fact that there is both reveal and hide, you're going to get the mean to be still small. So this is a so this particular profile is a pessimist Nash equilibrium. So it may not exist in globally uniform, but you might have uniform profiles which are essential. Okay, so there are a few things which kind of the reason why I gave the example is because it kind of illustrates a few things which are more general. One is that these games have this particular structure, right? I'm only using this KW on these propositions. So I'm not directly using propositions. I'm only using these KW kind of thing. So that is one observation. And the other is, I was saying that, well, in maximal, you just need to look at these globally uniform. You know, so there is nothing special about this particular example. It turns out that that is in general that's the case. So the fragment, these are called knowing whether formulas. The fragment is you don't directly make any assertions on propositions, but you always kind of guard it with the knowing whether operator. And the rest is fine. You have negation, you have disjunction. You could also put a ki here, but it's redundant. You don't need that. So essentially, you can't make any propositional assertions. You can only make an assertion about something is being shown. The consequence is quite clear. As far as the satisfiability of a formula is concerned, the valuation does not matter. Right? So it only depends on the strategy profile. That's one consequence of this. Okay, so
You have 15 minutes left.
15 minutes. Okay. Right. So this is a general result that you can show that if you're looking at this knowing whether fragment, where you cannot make assertions about propositions, but you are always guarding the proposition, then if there is a maximal Nash equilibrium, a uniform profile which is a maximum Nash equilibrium, then you can simply pick any strategy in that profile and then set it to be the globally uniform strategy profile, which is to say that I don't really care. I set every valuation to be this particular profile. That is also going to be a maximum Nash. This holds for only for knowing whether tapes. And the consequence is that if the set of max Nash equilibriums in the game is not empty, then there's always one which is reasonably simple, which is of this form where it's a globally uniform. So you don't really have to distinguish between the dimensions. Okay, so that is one thing. And the other thing that we observed in this example was that see, this is a two-player game with this knowing whether kind of formulas. And then I showed you a particular equilibrium, which is a pessimistic. Which is not a globally uniform strategy, but there is one. Turns out that, again, this is nothing special about this game. There is always going to be a pessimist Nash equilibrium for two-player games. The reason for that is also very simple. or intuitively that's.
This knowing whether it is important that the knowing method is applied only to propositions and not to.
Not to the formula.
Not.
Yeah. So you can include KI on the formula, but that you can show is yeah. So the knowing whether is on the propositions. Right. So the statement is that if you're looking at only two-player games, the knowing whether fragment of two-player games, then business national living always exists. So essentially, the example that we saw that you can force a min to be 0 can be different for any game. It's not just for that particular example. That's essentially the argument. And the reason why that works is because in a two-player game, whether you reveal something or not, you can think of it as a valuation. So there are only two players. So whether I have a set of propositions and whether I'm going to reveal some subset of propositions to you, I can think of it as a valuation. Right? All the propositions that I reveal assign to true, all the propositions that I don't reveal assign to false. Right? So what you can show is there is a bijection between the set of valuations and the set of strategies in this particular setting. And therefore, you can show that you can always force them into be 0 and the business natural. Okay. Right. So that is the game model. Now there are questions about existence that we can ask. There are some in this specific case of two-player KW games, I gave some I gave a statement about existence. But in general, what happens, right? And there's also this this question about Boolean games are a very well-known, well-studied fragment of games where you have in the study setting where you have Boolean goals. This is a well-studied game. So it turns out that Boolean games form a fragment of the framework that you are looking at. So let me just mention that. So Boolean games, the setting is very similar to what we are looking at, except that here you have only Boolean formulas. You don't have the KI operator, you just have Boolean formulas. Yeah. And the strategies are slightly different. So each player controls a set of propositions, so which means that he can pick a valuation for a set of propositions. Right? So it's not about revealing propositions, but it's actually about picking valuations for the propositions. So you have a strategy is like a valuation function for the set of propositions that the player controls. Now, when you're looking at a profile of strategies, what it defines is a valuation for the entire set of propositions. So okay, so what we can do, what we can show is that you can actually translate Boolean games into as a fragment into this observation games within the knowing whether games. The reason why this works is again to think of these valuations as some sort of interaction between two players. Yeah. So you have a set of n players, right? So you think of it as the n players being ordered in some fashion, right? So 1 to n, yeah. And so in a Boolean game, players are picking valuations for the propositions that they control, right? You translate it into in the observation game, what we are going to say is that picking a valuation corresponds to informing player 2 the value for these propositions. Yeah. So just use the correspondence between valuations and two-player setting. You fix an ordering of these players and then simply translate the valuations into as showing the propositions to the next player in this order. So this you can do, and essentially what you can show is that so you have the set of all valuations over propositions on one side, and you can map everything into these globally uniform strategies on the other side. Now, the set of globally uniform strategies can be much larger than the set of propositions, simply because you don't care about what happens to the other players. But you can define an equivalence relation on this set of globally uniform strategies, such that you can set up a map which is a bijection between valuations and this equivalence class. And every point in this equivalence class will have the same, so it will be payoff equivalent. So every point in this equivalence class will be payoff equivalent for all the players. So in terms of utilities, they are all going to be the same. And you can set up a map between evaluations and the equivalence classes in this space. So as a consequence, what you can show is that given a Boolean game, you can kind of embed it into a knowing whether game in such a way that the set of Nash equilibria in the Boolean game is not empty if and only if the set of the max Nash equilibria in the knowing whether game is not. So you can actually identify the precise fragment of Boolean games, which happens to be this knowing whether fragment. Okay, so that is one thing. I'll just mention a couple of things about the existence. So it turns out that one of the important parameters in existence of equilibria is what kind of epistemic assertions that you are allowed to make on players. Yeah. Based on this, we can define what I call these types for players. So the definition is very simple. You pick a player, you say that, so you look at what kind of assertions the player is making, so if there exists some player J such that player I makes a positive epistemic assertion about a variable assigned to player J in the goal formula, then you say plus is in the type. So essentially saying that I want to know something about I want to know some propositions that you control. And I want, so that's like a positive assertion, right? So if that's the case, then I define certain types, I add plus into the type of it. Similarly, if I make some negative assertion about the proposition controlled by some other player, then I add minus to this type.
So what did I make a positive assertion?
Right. So I have a goal formula where I have these k operators. Right. So if I say something like ki of pj, is saying that I want to know pj. Yeah. So that's what I mean by the positive assertion.
Okay.
I want to know pj.
I see.
Yeah. And I can also say not of ki pj, which is like the negation. I don't want to know pj. So my goal could be I want to know your variable. My goal could also be I don't want to. So that is the positive end. Okay, and you can also have goals which says that I want to reveal some variable to you. Yeah. So and similarly, I don't want to reveal some variable. So that is the C plus and C minus. So if I say that I want to reveal something to somebody else, then it's like C plus, and if I don't want to reveal, then it's like C minus. Yeah. So okay, so it turns out that the kind of assertions that you're allowed to make in the goal formula is important in terms of existence of equilibrium. And what you can say is the following: that if you have a game where you restrict that all players, for all players, the number of types is at most 3, then pessimist and optimist always exists. So I mean, it's not really magic happening here. There is a very simple reason why this is true. So let's look at, let's say, C plus, right? C plus is saying that I want to reveal something to you. That's my goal. Yeah. If I don't have C plus in my type, yeah, then revealing everything. Sorry. So if I don't have C plus in my type, then not revealing anything is like a dominant strategy. Yeah. So if my goal doesn't say that I want to reveal something to you, then don't reveal anything. That's going to be a dominant strategy. Similarly, if C minus is not there, then revealing everything is a dominant strategy. So, and all these cannot be there together, in which case the only other interesting possibility is, so you need to have C plus and C minus, otherwise there's an easy switch, right? And now if you restrict the cardinality of this type to be at most 3, then you can only have either plus or minus. You cannot have both. In that case, you can kind of do a fixed point computation over these partial strategies and converge to one strategy. So that's essentially the argument. Yeah, so the way I stated, it looks very magical, but there is a very simple reason why this works. And this is also tight in the sense that there are examples where you can show examples where if you have the type to be 4, then it may not have basically so. Okay, so this is one thing. Now, if you restrict to the knowing weather fragment, you get some better results, but let's skip that. The other thing is, yeah, just let me just mention about these decision questions, right? This is where I started with. So I'll just mention this and I stop. So another 5 minutes is okay. Okay, so these are the two questions: verification, which is given a uniform strategy profile, and for whatever is the decision rule, I want to check whether the profile is an equilibrium. Like this. And the equilibrium check is the same thing, but I want to check whether the set of Nash equilibriums for whatever is the decision. So what we can give is some tight bounds for the max decision rule. Okay, so the first thing to observe is that, observation games, right? This game itself, it has a compact representation on the parameters. So you have set of players, you have propositions, let's say some set of propositions. Now, a strategy is like a map from n to the power set of PL. So each strategy has a compact representation in terms of the number of players and the number of propositions. Or it's just n times k. But a uniform strategy is more complicated, right? Because it's a function from the set of valuations to the set of strategies. So this object, you can encode it as a Boolean formula, but then that Boolean formula will be exponential. So strategies are fine. It has a compact representation, but uniform strategies are very okay. So the first statement is that if you're looking at this language, this epistemic language that you're talking about, and if you want to do this check, this is called the model checking problem, right? So given a valuation and the strategy profile, I want to check whether the formula holds.
So what was LK? That is with the knowledge that.
Right, that has the knowledge of it. So that is the full language that so checking this is piecewise complete. Now, okay, so if you look at standard model logic like S5 and also model checking is polynomial time. The reason why this becomes difficult here is because so in a model logic, typically you have a transition system. That's it. Here we don't have the transition system explicitly, we just have one valuation. And so the trip case structure is not explicitly part of the input, it has one valuation, and that is the reason why this becomes more problem. So this can be shown to be piecewise complete. And
so this requires computing an exponential size triplet structure.
Yeah, because you might have to enumerate over all possible W's, right? Because of the ki operator, and that can be exponential. In a standard S5 semantics, that structure is dual tree. So that's a lot of input, so that's why it becomes one. Okay. Right. So using that, we can show that the verification question is also piecewise complete. At least the membership in piecewise is not very see. Well, the membership is so what you can do is check that given observation game and the uniform strategy profile, you can check if it is not in max any max of G. By doing the following, you simply guess a player, you guess a valuation, and guess a strategy. So all of these have polynomial representations, right? So that triple has a compact, so it's a compact witness that you have, and then you just have to check whether the utility is more. And this part you can do using the model by doing the model. Okay, so this is one, and the other is the emptiness check. This turns out to be NXP time complete. So the again membership is not very difficult to see. You can also show the lower bound using what are called these. This is again a well-known NXP time complete problem. It's called the dependency quantifier Boolean formula again. So maybe I won't get into that. I explain that, and I will just Right. So essentially, just to summarize, what we did was if um, define a game model which kind of captures incomplete information. It stays within strategy games, but we are looking at fragments of strategy games. It also has incomplete information. Using a logical language, so these are qualitative objectives, and then we define one notion of equilibria. So the outcome relation, well, we picked some, we essentially picked three outcome relations and looked at the associated set of Nash equilibria. We looked at existence of equilibria and also the computational questions, so verification activities. There are various things which can be modified. For instance, as Kavita was mentioning, the fact that these propositional variables, these are common knowledge. The valuations are not common knowledge, but the variables itself are common knowledge. And the communication is also common knowledge. What you don't know is the valuation. So that part, that's our model. Now you can change that, right? When you change that, you get a more involved model. So
You change the sense for.
right. So even the variables may not be common knowledge. And in particular, the communication. So when that S, that profile S, everyone knows which are the set of variables that you're communicating. What they don't know is the value. Okay. That you can change. And then of course the results will also change. The outcome rules that we picked were purely qualitative. Of course, you can try to look at a more quantitative kind of an outcome rule. I mean, we identified some fragments where equilibrium exists, but I mean, it's not like a characterization. So there might be better ones. And also fragments where the computational results are better. Okay, so you can also look at, so this is a one-shot case. You can also look at the iterative case, what happens to that. And then you can look at some variant of LPL with knowledge. See instead. You can also look at this incentive engineering sort of thing where you use taxation to ensure that certain particular outcomes are always achieved. Right, so there are various possible directions, and of course, even within what we looked at, there are many empty spaces. Right? So yeah, that's it. So I'll stop here. Does you have any answer questions?
Any question?
I had a question. What is I remember you gave one example. What is the high level motivation for formalizing this way? What is the setting that you're trying to capture?
Right. So it's a model where so imperfect information has been looked at a lot, quite significantly in so it's like a intersection of computer science and game theory, right? So the interiors are not really interested in qualitative games, and they are not even interested in computation. It's all about existence questions. For computer scientists, the computational questions become interesting. And within the qualitative setting, using a logical language makes sense. So we are looking at what we wanted to do is look at this fragment of incomplete information. It's not just incomplete. Your qualitative semantics for it. And identify cases where equilibrium models exist. So many of these, I mean, there are many applications for these kind of specification languages. So in a distributed system, let's say. So typically, or in a genuine distributed system, no one knows the global state of the system. So if you are doing some sort of planning over such a domain, right? I mean, typically the planning is there's a joint player sitting on top and then kind of doing the planning and right? That's not really distributed system. If you want to genuinely work with distributed plans, then these knowledge assertions are very natural because you're saying my goal might be that I don't want to reveal something, or my goal might be I want to know everything about you in these kind of things. So that's a very natural game theoretic setting where you have these satisfying components. That kind of works in the iterative case. We have some results in the iterative case. That's the more natural setting. So temporal and epistemic operators together. This one is set. Okay.
Okay, so if you have no more questions, let's thank Sunil. Yeah. Sunil is here until the afternoon. Just, not talking. So,
Questions over Zoom or?
can we see the chat? So we just.
No, I'm good. Yeah. The chat was just me, probably.